And we can even do like one or two at a time, right? We don't even have to do all, whatever, 10 of them that there are. Yeah, but we can make our way like you so that it's broken up. You know, you don't have to do them all at once too. Okay. Yeah, that works. Okay, cool. Yeah. Yeah. Okay. Uh, yes. Okay. Okay. So I think sort of the best place to start is to sort of ask what or even why energy. Yeah, what is energy? And like why do we sort of what are we doing here? Why do we you know, why is it useful to look at energy and what is this thing energy? What is energy? So you should be able to sort of answer this is definitely a test type question. So when force is exerted, okay, I like that. When force is exerted. Mm-hmm. Yes, yes, but you wait, you said work. I'm asking what is energy? So, okay, so I would be more comfortable with what is work here, right? But this doesn't necessarily have to be when force is exerted. So, for example, you know, if something is making sound, does it have energy? How do you know? They're what? Yeah, the vibration of, you know, air, the medium between us, is sound. That's what sound is. So, what about it? What does it have to do with energy? Is it a okay? It's moving the air, right? So it's a form of energy, is what you're saying. So, how do I know that that thing producing the sound has energy then? It's not just it's energy total, it's energy bank account, right? Let's think of its energy bank account. Is the, you know, little bird, for example, is the energy bank account of the little bird close to zero? It is a billion, you know, what is it? Is it a non-zero number? Is it zero or what? Is it negative? Is it positive? What do you think? This little bird that can make sound. Let's say that it's totally like devoid of all life and is just this little like robotic thing that can just make sound. Let's just think about the sound energy. Is the energy bank account of that bird, if it's just sitting on a table, sitting still, it's not moving, but it's making sound? Is it zero? Is it negative? Is it positive? What do you think? It's not going to be too crazy a number, sure. How do I know it's positive and not zero or negative? Just like a bonfire. Let's think of another example. A bonfire. Surely the energy that's in the bonfire is quite a bit. How do I know? Because it's coming out as heat. It's heating all the air molecules around it. It's coming out as light, right? It's coming off as sound, the crackling, right? So that's a lot of energy that has to come from somewhere. So its energy bank account must have been not zero, must have been positive before it released this energy, right? So the only way I know that something has energy is if it shows me by doing something. What is the doing something? What is the word for the doing something? Yes. So energy and work are very, very closely tied, but energy is the ability to give off. Like, I know that you have energy. This is almost like a sentence that you need to say every time. I can see energy and prove that energy is there because I can see it coming off. I can feel heat. I can see light. I can hear sound. I can see all these sources of energy that are coming out. I can see it moving, right? Therefore, it has energy, right? Okay. So when force is exerted or when something is being done, right? But can work be a positive and a negative? Let me ask you that first. The next question that's coming that may make this easier is this a scalar or a vector? What's the difference between a scalar and a vector? Yes. Let me give you a simpler example. Like 3 balls, or 3 beanbags, or 3 pens. That's a scalar. You can't have 3 pens north, right? Unless you're using the pens as a source of measurement, in which case you're kind of cheating, and really it's this amount of centimeters, right? But 3 pens doesn't have a direction. It doesn't make sense to have a direction, right? So that's why I think it's better than the speed versus velocity one, because speed could very easily have a north and mean something, right? But 3 beanbags south doesn't really mean anything, right? But 3 beanbags is just a count of something, a magnitude and a unit. So direction, does work have a direction? Is it 60 joules in this direction? No. It's just something that we can count as if it's a bank account for 2 objects, and the total always has to be the total. You can't invent money and you can't lose money, right? Okay, what we just said was the law of conservation of energy. What did I say? Yeah. Can't create energy or destroy it. Right? You can only do what? Because somebody might say, "Hey, look, you went from $100 to $80, so you just destroyed some money. You can spend it." But what is spending? If I'm going to do the accounting of energy, like I'm going to do the accounting of money, I have to include the first party that gains some money, right? And then the total between both of us will always be the same, right? Do you agree? So you can only transfer energy. You can't create it or destroy it, you can only transfer it, just like money. It's easy to sort of use the money analogy, okay? And a lot of it is like you have to pay energy. So for example, to get molecules to do crazy things that they don't want to do, all I have to do is pump up the energy. I can increase the temperature and get them to do crazy things because it's like paying them to do things, right? And when you take them down to really low temperatures, it's sort of like they're sort of really, really trying to conserve energy, so they go into this really slow state. They're not moving. They're doing that's solids, right? That's what happens. That's the world of energy. So one big conversion we're going to be looking at is kinetic energy, which is what? How do I know that kinetic energy exists? Yeah, but how do I know that moving is a form of energy, a source of energy, that there's energy there? How do I know that? Again, what's the only proof that I know that there's energy somewhere here? How do I know that you have money? If you spend it. Yeah? That's the only way in the energy world. That's the only way I know if you have money. I can't look in your pocket and see how much money you have. Okay? So that's the same analogy for energy and for every object. Okay? Now some objects have a hidden source of energy. So for example, this pen, is sitting here, right? And now suddenly it's moving. Where did it get that energy from? You can't create it. Where did it get that energy from? But if you sort of so like let's take it the second after I let go, right? The very second after I let go. It's going okay, yeah, sure, it's even moving. It's going very slow. But then here it's going pretty fast. Right? So where did it get that energy from? It increased its speed. Where did it get that energy from? Because I wasn't touching it between there after I let go, and then it was moving a little bit, and then it really started moving fast. Where did it get that energy from? What's causing it to move down? Gravity. There must be some bit of energy that's in the bank account that I can't see until I let it do the thing that it wants to do for gravity, the thing that is sort of like lower energy for gravity because it has to spend some of that energy to create speed, right? So, or it wants to, or whatever, it happens. We don't have to anthropomorphize it that much, right? So, okay, so then what is that called? Do you know what that sort of stored energy is called? It's got a word. And it's got a really bright future. Yeah. It's got it's going to turn out to do great things. It's got a lot of yes, nice. Okay. So potential energy means this stored up energy that I can't quite see, that suddenly it releases, right? Is kinetic energy a potential energy? Can kinetic energy be hidden? Is another way to say that question. Do you always see kinetic energy? Not where it came from, but once it's there. Yeah, you do, right? Like you can see things that are moving, right? Okay. Can you always see things that have gravitational potential energy? That have the ability to fall? You can always tell when something has the ability to fall? No. Yes, you can see the object. But you don't necessarily... So the hidden factor there is the potential energy, right? And there's also a chemical potential energy that I could transfer into light, heat, sound by burning the pen and turning the splitting up all the carbon molecules into carbon dioxide and burning it till it disintegrates, right? So that's a form of energy release that I mean, most things they sort of have a bank account that they can't really reach of chemical. Most things don't get burned, let's say, right? That might decompose, and that's another form of kind of giving off energy. And it does. When you go into like a mushroom forest that's doing a lot of decomposing, the ground gets pretty warm because there's a lot of energy releasing. And in fact, they live off that energy. That's what that is, right? Is decomposers live off that energy. Okay, so but regardless, like that's another energy transfer, right? So you should always be ready to talk about energy transfers. Give me 3 energy transfers that happened today in your life. Energy transfer. So you give me this sort of like energy from this to this, and we'll talk about maybe how much energy was the transfer. Did you? Yeah. Did you move at all today? Did you drop anything today? Did you pick anything up today? Did you hear anything today? Did you see anything today, right? Like those are all energy transfers in some way. Like that's kind of how you interact with the world. Is like energy comes into your eyes and you turn that energy into light and you make an image of it, right? And you hear things. That's the receiving of energy there, right? And like so give me like, okay, start with one example of an energy transfer that happened today in your life. Okay, awesome. So how far did you drive? Okay, so let's say, okay, so that's awesome. It's good to hear that it took 30 minutes. Okay, because we'll now sort of do some per time thing here, right? And it was how many kilometers? Like let's say 20 kilometers. Let's that's not that fast actually, but that's like 40 kilometers an hour. Were you going like pretty slow, medium fast? Okay. Oh, that's pretty good. Okay, 60. So, but you stopped a bunch and stuff, so like that's there's also that, right? But let's just say you go 60 kilometers in 30 minutes, right? So that's like no. So that's sorry, 30 kilometers in 30 minutes, right? Which is 60 kilometers an hour, which is in meters per second. Remember, we can divide by 3.6. 3.6 is the conversion between them, and meters per second are always, the number is always smaller. So let's just quickly divide by 3.6. And we get 1.67. No, 16.7. Okay. So that was your speed, right? And you did that over this amount of, okay, so let's sort of like look at some of the energies of this. So one work equation that we should always already be comfortable with is this. What is this? Yes. What sort of things are going to, be equal to energy here? Kinetic energy, sure. Yeah, so we can see delta E in kinetic energy, right? So we should sort of like, and I mean, what you did here is really you're sort of fighting against the, if you could have gotten your car in space to going this speed, you could have put no gas into the car for the rest of the trip once you were going this speed, right? The reason you sort of had to like hit the brake and hit the gas was because you were fighting against the friction on the road, and you might have been stopping, wanting to stop, right, and change your speed, right? But like let's just say that you sort of like put the energy into getting up to this speed, okay? So in the initial sort of like draw up, you were just getting up to this speed, and let's just say this, you hit this speed for 30 minutes. Perfect, right? You're on a track, okay? So how much energy would that represent in terms of an energy change? Well, you're sort of from state 1 to state 2, from time shot 1 to time shot 2 was you were going 0 meters per second. What's the energy equation for kinetic energy? Do you know kinetic energy equation? The general equation? 1/2. Yes, nice, good. Okay, so how much energy did the thing have in E2 at the spot 2, or EK2, I guess we can call this? Exactly. Yeah. 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 So I like to do 1 and 2 because I can now I can do 3, and then I can do 2 and 3, and I don't have to say this final thing was now my initial thing, and my initial is now the new final. You know. So that's just the notation that I like, but it's okay to use initial final too, right? Is that what you're sort of used to? Okay. Sure. Sure. Let's do it. So you initially were in this state, and you're finally in this state. Okay, so what is the kinetic energy equation at this spot where you're going 16.7 meters per second? It's 1/2 mv squared. It's always at 1/2 mv squared, in fact. But your m's and your v's might change, right? Do your m's ever change? No. So let's just say m, right? Or m over 2, because the 1 over 2 will never move either, right? That's never going anywhere. So what you end up with is your sort of v final squared minus v initial squared. Do you agree? In terms of the math, what did I do there? I factored out the m over 2, right? Okay, so what's v final? Good. Okay. And what's v initial? Good. Okay, so let's just say that, let's just find out what that number is. 16.7 squared is, and then we can divide that by 2 actually. So we'll say it's about 140 m. Okay? Okay. Now this is something that we'll often see. In these energy questions, sometimes you won't be given mass. And you're like, wait, what? Like, most of these equations have mass in them, right? So how am I not going to be given mass? Well, because most of them have m in them, it factors out so many times on both sides of an equation, right? So let's say, for example, we were going to use this energy that you drove your car. Let's say we're going to use this to go up a ramp and see how high you could get up a ramp. You're not going to go off the ramp, you're just going to go up, and then you're going to come safely down, okay? But what we're going to do is we're going to measure your height, okay? So we're going to see how high up this sort of like long ramp, and you're going to end up, you know, somewhere around here, let's say. Okay? Oh god, my car drawing ability is not great, but so this is your sort of V initial, which is 16.7 meters per second, right? That's going to be our V initial. Our V final here is going to be what? Yeah, right when we get to our peak of the hill. Yeah, good. That's nice. Okay, so what we can do is we can sort of turn this into a height question. What major energy source then? Like we're using up kinetic energy, aren't we? It's disappearing, right? Can you see that, or is it potential energy? Can you see what the kinetic energy is sort of like being transferred into? Is it visible? Is it easily visible? Is it, yeah, it's getting hotter, it's making sound, it's um, creating light, it's doing something that you can see, or it's doing something you can't see. My question is it hidden or is it not hidden? Is it potential or is it not potential? Is it stored or is it not stored? It's not potential. Why? What is it going into? I would say the kinetic energy is kind of going towards the movement side of things, right? I maybe am with you if you say vertical, purely vertical movement, right? Because the horizontal, it can go 16.7 for as long as it wants. The thing that's causing it to slow down is it's going up a hill. Why does that take energy? Why does it take energy to go up a hill? Yes, but why does that take energy? It's not friction you're fighting against. Who is it that you're fighting against to go up and down? Who's the who? Yes, yes, good, good, good. So there must be some currency of gravity that you're gaining, that you're this is the opposite of your bank account from gravity going down to create speed. You can also throw things up or just, see them rise. And the reason they're slowing down is because they're giving that energy back. They're giving that kinetic energy back to store up some kinetic, some gravitational potential energy, right? So this H value is a potential energy. It represents a potential energy. And almost all forces, so kinetic energy is not necessarily one, but a lot of, sorry, not forces, I'm already thinking forces, because a lot of energy equations just simplify to be force times the distance. Because the work, a really, really common work formula is force times delta D, which is how far did a force move something, and that takes energy. We can see how much energy that took by saying what was the force you were applying, how far did you get with applying that force, and we can use that to calculate work and actual energy. Okay, and then we can also see, wait a second, you were pushing it this much, but there was friction, so you had to sort of like push it harder than its distance improving, because you were also giving something up to friction, to heat, to sound, right? It was making a little shh as you were pushing it. So there's wasted energy too, right? So we're going to have to do the accounting of energy, and wasted energy is going to be in there. We're going to just basically say, like, this is the wasted bin, and I don't really know much about it, but like it lost it's only actually 84% of its total because we lost 16% of it. Like that's how you're going to treat the wasted energy section. And then all these other ones, you're going to say, this is the amount in gravitational potential energy, this is the amount in kinetic energy, this is the amount in um, uh, chemical stored energy. This is the amount in elastic potential energy. What is elastic potential energy? Elastic potential energy. So we know what energy is now. It is what? Wait, what's the definition? Maybe we didn't nail it down actually at the start. For sure, for sure, for sure. Energy. What is energy? If I ask you what is energy, you should be able to say, uh, quick little sentence. The the ability to do work. That's it. Yeah. That's your like good textbook definition. Okay? It's the ability to do work. And that's how I can tell that something has energy is because it can do work if it wanted to. Right? For sure. Oh yeah, yeah, that's easy too. Right. Exactly. Yeah. The ability to do work, right? Like yeah, like that's a great way to sort of like bring it to something that makes sense too and is connected, right? Like awesome memory tip is to connect things that you already have connections with, right? Like so you already might think of a particular carrot and a broccoli because of your favorite dish, and so like you can use carrot and broccoli to like link two chemistry things that start with a B and a right. Like you can do that, right? So you take advantage of that as much as possible, right? And this is part of that thing I was talking about with like acronyms, right? Like you can make them funny, you can make them goofy, right? And it works better because you remember them because it's funny, right? More than like some boring thing. Okay, so gravitational potential energy is a force times a distance. Well, what is the force of gravitational potential energy? What force could possibly be here? Of gravity? Gravitation. Well, we're going to come up with the energy equation for gravitational potential energy, for how much energy is stored in an object. So it's and really what we're sort of doing here is saying delta, the change in gravitational potential energy. Because what you and I do is sort of like a cheat, and we'll talk about that in a second, but we only are going to look at the change in gravitational potential energy. And the force of gravitational potential energy, the force that I have to lift things up, right? Because I invest energy, and what force do I have to sort of like fight against in the free body diagram? It's gravity, right? So in some way, I sort of invest it with this force, and what distance do I act upon? Like what distance does that force act upon, or like affect? It's the delta H, right? It's the delta H that I see here, right? Well, Fg is mg, so this is going to be mg delta H. That is the change in gravitational potential energy of objects on Earth, because it's g, right? And so let's say that we were using this 16.7, and you had 140 m worth of energy to invest. That's what that kinetic energy is there, right? How high would you get up the ramp? What would be your delta H? And 140 meters, close. Put it into an equation on your page. You might see something different. What did you just do? Remember, this is m, not meters. This is like, m1, right? And this is m1. Same m1, right? We just don't know what it is. Yeah, that's right. Good, but equal to what? Like you need an equation there, don't you? We don't have mass. Okay, but put it in an equation, and and let's sort of talk about us not having mass in a second. Once you have something on your page. This is something that's so common in these energy equations. Because m is in every equation, it's oftentimes going to cancel on both sides. So it might feel like you're like, wait, what? How do I do this without m? Put it in an equation before you start to get those feelings or like really act on those feelings. Like it's okay to have those feelings and it's good that you're noticing it. But then put them into an equation because you'll see the m1s cancel. Oh, close. Did you do that rearrangement in your head? Did you get to this stage and then do the rearrangement in your head? Oh, gosh, just because look how fast we can sort of do this. Like faster than we sort of like think through it. This is 9.8, even if I write 10, right? Not 2 because it's G, right? So it's 10. So delta H divided by this divided by 10. So this side has to get divided by 10. Delta H is 140. Or sorry, 114. Are you with me on that? Yeah? So, okay. Yeah, so this is a simple, like I didn't really talk about sort of how we got here. This was instinct. This equation that you came up with, right? What did we say here? What's the sort of equation above this? Because this was delta EK. So what's on this side? Do you remember? Yes, nice. Good. And so what we're saying here is that the change in gravitational potential energy that you see in the bank account of gravity and what I owe and can spend with gravity, the change there is going to be equal to the change that I see, and there's a direction difference, like one goes up, the other one goes down, and vice versa, but the values are going to be equal. How much it goes up here is going to be equal to how much it goes down there, and vice versa, right? This is the equation version of the law of conservation of energy. Because what we're doing here is we're sort of saying, and this is the buildup that you can, if you want to, you can always add this and it makes the problem really easy if you take this sort of like simple approach. The total energy at the start is equal to the total energy at the end, right? Do you agree? This is like saying the total amount of money that two people have is the same, and then they're going to exchange some, but the total amount of money they have. They might have different currencies. So they might have American and Canadian, right? Which means they could have EK and they could have EG, and then they could sort of, see some conversion between them. So let's say this, we're going to use initial. Yeah. Okay. So this is like the accounting. Remember, we said we're going to do the accounting of energy on both in two circumstances, right? We're going to see the conversion between them. So with this, I can do a little rearrangement, and this is just because of the perfect sort of world that I live in here of this rearrangement, and that it's totally, the amount that goes into one versus the other, is I could move this over to this side, right? And move this over to this side, right? And what do we get? Well, this one is okay. This one is delta EG because it's a final minus initial, right? But this other one is initial minus final. Is that okay? No. What actually happens here is, this negative value is true of this equation. I kind of lied when I said this, and this is maybe something that we could say, okay? And this is something that's important and easy about energy that seems hard. Is negative signs always just mean from you to me instead of me to you? It just means the opposite direction, okay? So that's very, very important about when negative signs show up. If you ever are like, wait, why is this negative here? It usually means either you've assumed like something is moving in one direction when it's moving in the other, and that's why the negative is showing up, or it just means that the thing is kind of like the opposite direction that you set it up, that it was positive to be, right? So in this example, we sort of said, okay, well, the delta EG is kind of the positive one, so this one's going to be the negative one in some sense. And this just means like it's converting into the other, right? Because one goes up, the other one goes down. So to make that equal, we have to put a negative there, right? Okay. But in terms of like one going up, the other one going down, if I just told you the value, you could do that math by saying it's speeding up. You wouldn't need to figure it out with equations. You'd be able to say the delta EK has to go up, right? Because it's speeding up. Its speed is getting it. So what I mean by that is you handle the negatives and the positives. You know what's going up, what's going down. Don't let the math tell you, oh, this is negative, so it's going down. Like you should be really, really sure that something's like kind of going down in some way to say that its value is negative, and if something's going up, say it's positive, right? Like be really sure of that in terms of direction and also like whether something's energy total is going up or down. Okay. Okay, so anyway, a little rant there, but like it's helpful for sort of negative signs. Those always screw up everyone, right? Like every mathematician gets screwed up by those, right? Okay, so yeah, okay, so delta H would be 14, right? Beautiful. Okay, so this is like, oftentimes a conversion that you're going to be doing. Another sort of like energy accounting that you need to be ready to do is this, any general force with any sort of general distance. So this is a perfect example of that. Okay. So take a second here. I'm going to just mute and give you a minute, okay? And see if you can try this problem. Have you seen this already? Have you tried this already? You maybe saw it in class or something? No? Okay. Okay, so then let's try it. So once you've sort of digested here for a second, can we just talk about what forces are responsible for the energy that we're going to do the accounting with? Okay. Okay. Well, is there? What sort of speeds do you see? So is the sled going to sort of like continue moving after this force is gone? Like in some way, so what that circumstance is like a projectile or somebody throwing something, right? Like that's adding kinetic energy to something. This is an example where we're just moving something, right? Something is kind of like constantly under the force of friction, and for a time we oppose it and give it some distance. We give it some delta D, right? What is the distance that we gave the sled? Yeah. What was the change in distance? Sorry, the change in displacement. Yeah, good. So we, sorry? Good, good. Yeah, so this delta D is sort of like connected to a force that's applying the delta D, right? And that is some work equation. So do we know that force? Okay, so now this is where we have to sort of talk here because we the force that is causing the delta D is the one that needs to be multiplied by the delta D here. Is the pulling up causing the horizontal motion? Is the pulling up of the sled? Because I'm pulling at an angle, and that's made up of a pulling up and a pulling sideways. And the thing is moving sideways purely. It's not moving up. It's not moving down, right? So, okay. So let's talk about the force of friction over that distance. Sure. We can talk that because that one is in the direction of this delta D, right? The friction is sort of this way, right? Okay. And it's 67 newtons. Okay. So what is that work there? So also, by the way, I don't want to sort of like, it's always helpful to see that attempt. So let's see that delta D because we're going to use that number anyway at some point. So let's do this, and this is 345. So let's get a number here and see, because it'll be interesting to kind of compare that to this amount of work here, right? Okay. So I actually have to get running also at about 7:45. Um, so yeah, we should be able to sort of get through this problem, and I can maybe direct you, but okay, perfect. So yeah, and if we want to, we can sort of set up some time to kind of like get some more practice in, or you now can go back and do some more practice and then come to me with like, okay, I had this one particular one that was like weird or whatever, right? Yeah. Okay, cool. Yeah. So that's sort of like where, yeah, I'm glad we sort of got through that, right? Okay, so yeah, so let's get some numbers here. So 133 times beautiful. Okay. So what's the unit? Nice. And here we have 67 times 345. So it's not going to be quite as much because it's not 135, right? Which I didn't write. I wrote 133, but is it half actually? Yeah, good. What's the unit? Beautiful. Okay. So all of the force didn't go towards moving this object, right? So we're now asked to calculate the work done by the hiker, the work done by friction. So we just calculated the work done by friction, right? You comfortable with that? Okay, so where does that energy go? Mm-hmm. Into the distance. What do you mean? I love if it's what you what I think you mean. I love it. It's like a poetic description of what I think it is. I love it. Just dissipates into the environment, right? Oh, I love it. Okay, cool. I've never heard that expression. Into the distance. Is that like just like fading into the sunset sort of thing? Is that what you imagine? Okay, yeah, sure. So yeah, exactly. It just kind of that's wasted energy, right? So we lose a bit of it. Okay. How much do we hold on to? Yes. The total work done on the sled. No, the total how much so okay, so what there was a transfer of energy, right? Who was the investor? Yep. What did it go towards? Or it doesn't go towards himself, no. But towards what? What are they investing their energy into? What are they giving it to? The sled. The sled, right? They're giving it to the sled. But they're also giving it to just the distance, the environment, right? So then we should be able to sort of like come up with an equation here of like work that goes in is equal to the work that kind of comes out, right? So they say calculate the work done by the hiker, the work done by friction, and the total work done on the sled. So let's kind of get some equation with those three things in it. What would the equation look like? Well, this is like the work of this is the work of the person going in. So this is the work done by the hiker, right? I guess is what we'll say. The work of the hiker is what goes in. And what does it turn into? Yes, good, yes. So let's say S for the sled, right? So there's work that goes into the sled, but then there's also that work that goes into the friction, right? Okay. So you should always be able to sort of do this like, energy investors versus energy receivers, right? Or like what does the energy go towards and who's giving it, right? Okay, so we have 2 of the 3 values now, so we should be able to find the third one, right? So this is the total that went in, and this is how much was sort of was going towards friction, then we should be able to do the accounting of how much was sort of like not used and went towards the sled, right? Okay, so yeah, so like it seems kind of complicated, and another way we could it should also work that we take the horizontal component of this friction vector, and we should be able to do some math with the friction as well, and see some free body diagrams showing us some equal forces there too. Okay. Okay, so yeah, so I would say like, jump into some questions now. If you do message me later, I can maybe get to some, if something pops up. But when are you thinking about meeting next?